So now that we've talked about each of these situations, let's take a look at each of our terms and how we actually calculate each one of these. Our mass terms are fairly simple. We're just looking at how much of a mass is entering or exiting our system, right? To do this, we look at the concentration of the contaminant, which is simply how much mass per unit volume there is of this contaminant, times our flow rate. Our flow rate is simply a volume over time. So this is the volume of water entering or exiting the system over time. And the concentration is how much of this substance is in that water. This reaction term is a little bit more tricky, so let's take a closer look at it. First, we'll simplify. Remember that our flow rate times our concentration was just a mass going in or out of the system. Well, in this case, we're just looking at some sort of change in the concentration. So we're looking at an accumulation or an exiting of the contaminant as well. We'll say this is like a change in concentration over a change in time. That's our R term. That's what R equals, the change in concentration over time. If we multiply R times volume, that gives us our flow rate, again, because volume over time is a flow times the concentration. So we said that the R term, part of our reaction term, is just the change in concentration over the change in time. Well, there's also another thing it equals. It can either equal R equals K, which is some constant, times our concentration to the nth power. Again, n is just some constant, and that's for generation, if we're making a contaminant. If we're talking about decay, where we're losing the contaminant, we simply just put a negative in front. And that's our R part of the reaction term.
However, the C in this equation can be impacted based on the type of flow we expect in our reactor. We divide reactors into three broad categories, the first of which is a batch reactor. So in a batch reactor, there's no flow in or out, and the solution is in the reactor for the same amount of time, and then the reactor is emptied and the cycle starts over again. So a good example of this is a closed system like a beaker on a lab bench. In the second scenario, plug flow is occurring. So the flow reactor is sized in order to provide sufficient hydraulic residence time for reactions to take place. Plug flow is where the velocity of the water is relatively constant at any point in the reactor. So it moves along at a constant velocity, kind of like a puck moving through a pipe is what you could imagine, is the little reaction that's taking place. So plug flow reactors are often used to represent things like rivers and pipes. The third type of reactor is a completely mixed flow reactor. So flow through the reactor is occurring and mixing is performed inside the reactor to speed up the reaction. CMFRs are typically used to represent things like a rapid mix chamber for alum addition at a drinking water treatment plant, or even into ponds or lakes. Each of these approaches impacts the concentration in the reactor at a given time. Thus, given our reactor and reaction rate equation, we can derive an equation for the ratio of the concentration in the reactor at any given time to the input concentration, and that is Ct over Cin. So this is at your time, and this is your starting concentration. Thankfully, the FE handbook clearly spells out the reactions that result from this derivation in each situation we could expect to see. Let's take a look at that. You can pause your video here, write down any equations you need. We'll leave it up. So as you can see, we typically expect our reaction order to be between 0 and 2. Depending on this and the reactor we use, we get different equations. Note that the equations for the 0th order are the same regardless of reactor type. This is because the concentration is not a factor in the reaction rate for this order. R simply equals K for generation and negative K for decay in 0 order. The only real difference between our batch reactors and flow reactors is that the T for batch is the time the water is held in the reactor before it is emptied, whereas the T for plug flow is the hydraulic residence time, or the time it takes any given drop of water to move through the reactor. Note that the hydraulic residence time is simply the volume divided by the flow, V over Q. And in your problems, you might need to rearrange this equation, so just keep it in mind. We can plug the hydraulic residence time formula into each of the equations to get equations for volume and or flow as shown here. You can see that these are the same equations as before, but V over Q is substituted for residence time and the equation is solved for V.
One other thing we have to factor in here is that temperature can also impact the rate of our reaction. We adjust for that by modifying the K constant. Our new K constant, we'll call it KT for K temperature, is just the standard K that we would use at 20 degrees Celsius, modified by a temperature coefficient, we'll denote this by theta, raised to the power of the temperature we're finding this K for, minus 20. Now, this theta can be either one of two things. Theta can be 1.135 for any temperatures between 4 to 20 degrees Celsius, or theta can be 1.056 for temperatures between 20 and 30 degrees Celsius. And that's how we correct for temperature. And there you have it. Now that we've looked at each term of our general equation, let's take a look at the big picture one more time. We have our accumulation equals mass in minus mass out, plus or minus some amount of reaction that's adding or taking away some amount of mass. Now we can find mass in and out by multiplying concentration by volume or flow rate, and we can calculate our reaction term using the FE provided equations for different reaction orders and reaction types. In our next video, we'll look at some example problems to help us get some practice with mass balancing. See you then.